Welcome to another mini lecture for Module 7 on hypothesis testing and two-sample designs. So we're still looking at the study of dialysis patient education and asking the question of, does a program education package on kidney function and renal failure improve dialysis patient knowledge? And now we're going to be looking at a second option to design this study. The second option, we're going to look at a group of patients who are on dialysis. Say we have 10 people who are on dialysis. And we're going to do a before and after study. So we're going to test people and their knowledge prior to the programmed education package, and then after receiving the program education package, we're going to test them again. This allows us to assess the knowledge of the people in the study both before and after the education package in order to ask the question again of, does a program education package improve dialysis patient knowledge? And this approach will control for the baseline knowledge of people, right? So whatever their baseline knowledge is, if we're thinking that this programmed education package will improve their knowledge, well then everybody's knowledge should, on average, improve and go up. They'd have a higher score. And this is a paired sample design, which would be analyzed by a paired sample t-test. And we use this approach when we're comparing two treatments on paired samples. So, for instance, here we have pre and post tests on the same person. We could also do something like have two skincare ointments applied to one person, one on each arm, right? So that's controlling for their lifestyle. It's controlling for, again, whatever genetic makeup might influence their need for some type of an ointment, for instance. And when we do a paired sample t-test, we're interested in comparing the mean of the difference in test scores from before and after the program for each person. So our null hypothesis here is that the mean difference would be equal to 0, so there'd be no effect of the education program because their score on the test would be exactly the same as it was prior to the test, right? So for an individual, their score would remain the same, and if their score is the same, then the difference would be 0. The alternative hypothesis is that it's different from 0. So it could go up because of the education program, or it could go down because of the education program. And the test statistic is really similar to what we looked at before with the two-sample t-test, but here now what we're doing is we have the mean of the differences minus 0, and it's minus 0 because in the way that we have our null hypothesis set up, we're comparing our mean difference to 0. In some other instances, you might have a different difference that you might expect, but in this case, it's our mean difference minus 0. And then on the denominator, we're now looking again just at the differences, so it's the standard deviation of the difference squared divided by the number of differences, so the number of pairs that we have in our sample, and then the square root of that. So the assumptions that we have for a paired sample t-test in general are that the data are independent or random samples from a population, so the people that are involved in the study were randomly sampled individuals who are on dialysis. We have paired samples, and that the differences are normally distributed. Now it's not that the data is normally distributed, it's that the differences are normally distributed. So for this example, we have to, as our first step, construct our statistical hypothesis. So again, that the mean population difference is equal to 0 for the null, and then it's not equal to 0 for the alternate hypothesis. Our independent variable is still education program, and now our dependent variable is what we measured, so now we're looking at the difference of the scores on the test. We have to establish a statistical decision rule. We're going to stick with alpha being equal to 0.05, and then we have to calculate our test statistic. And to do that, we need to collect data. So here's a table of data. We have patient numbers from 1 through 10 on the column to the far left. The next column looks at the before instruction values for each of those individuals, and you can see there's a bunch of range here, and then we have the after instruction values. Okay, so these values, we can see the mean and standard deviation for those, but we're not interested in the mean and standard deviation for each of those columns because we're interested in controlling for individuals and what their knowledge was going in. Because if someone's knowledge was high, so we have some individuals at 77, You know, they can't improve by a score of 30 because then they'd have over 100, but they should still improve. Okay, so we have our before and after. What we're interested in is the difference. So we would take before and subtract after. So if individuals did better afterwards, then that would be a negative score. That means they had lower knowledge before the instruction. And at the bottom of that column for the differences, you can see the mean and the standard deviation. And that's the information that we're going to use in calculating our paired sample t-test, right? So the mean and the standard deviation of the differences is what's key here. So let's work through this. So here we have our paired sample t-test, our statistical hypothesis that we've already discussed, our statistical decision rule with an alpha of 0.05, and we're going to calculate our test statistic as the next step. So we have 10 pairs, so we have 10 individuals that have data for both before and after. Our mean difference in their score is negative 16.8, and our standard deviation from the sample is 13.4. And here is our calculation for our t-statistic. So our mean difference is negative 16.8 minus 0. And then in our denominator, we're going to have 13.4. We're going to square that, and then we're dividing it by the number of pairs, right? Because those are the number of independent samples that we have. So this is going to be negative 16.8 divided by square root of 179.56 divided by 10, and then the square root of all that on the denominator, which is going to be equal to minus 16.8 divided by 4.237, which is going to be equal to negative 3.965. Again, we have a two-tailed test that we're doing, so the negative will not be a factor here. Okay, so we have our value for our t-statistic, and you should know what our next step is. That's to compare our test statistic with our decision rule, and then draw a statistical conclusion about our null hypothesis. So we need to figure out our degrees of freedom. This time, our degrees of freedom is based on the number of pairs minus 1, and it's minus 1 because we only had to estimate one mean from the data that we have. So that's the mean of the differences. Whereas in the two-sample t-test, we had to estimate two means from samples, one of the means for each of the treatment groups that we had. So our number of pairs minus 1 is 10 minus 1, which is going to be equal to 9, and our value of alpha is the standard of 0.05. So we go to our t-distribution. Again, we're still doing a two-tailed test at 0.05. Our degrees of freedom is 9, so our critical value of t is 2.262. So our critical value of t is equal to 2.262. We're going to draw our distribution. We're going to put in our critical values. I always think it's a good idea to label underneath which value you're looking at. Otherwise, that can get a little confusing. Recall again that if our t-statistic that we calculated falls into the tails, that means it's in the rejection region, and if it's in the middle portion, it's going to be retained. Our t-statistic that we calculated is negative 3.965. That's our t-statistic. And it's falling in the rejection region out here, which means we're going to reject our null hypothesis. So now our absolute value of 3.965, which is our t-statistic, is greater than, because it's in the tails, our absolute value of our critical t-value. Therefore, we're going to reject our null hypothesis. And when we reject our null hypothesis, that means that the mean difference in the score before and after the education program is significantly different from 0. And our p-value is less than 0.05. So the probability that observing this difference from 0 due to just random chance is less than 5%. So our conclusion again is that the mean difference in the score before and after the education program is significantly different from 0. When we look at our data, right, we know that the values we have here are the before minus after. So people did better after, and we can see that the education program improved their scores. So our statistics, our conclusion from our t-statistic will tell us whether or not we retain the null hypothesis or reject it. We have to go back and look at our data again to see what that actual direction is. And that's important. So in the paired design for option number 2, there are strengths in this design, and is that we can control for variation among our replicates. So if maybe some people had done some research on their own before the study was done, they would have a higher baseline score, but they should still likely learn more. And if we just had some random people sampled in each of the treatments, like we did for the first analysis in the independent samples, you cannot control for that. So in some cases, the paired design, where it's possible, can give you more power.